All right, so this one, we also have a non-rectangular region, right? We don't have a rectangle here, and so it's a little more complicated, but hopefully you see here that what I'd want to do to make this as easy as possible, I'd want to go from this side to this side, because that's going to give me my x values. My x values are the ones that are kind of complicated here, you know what I'm saying? Because the y values, I can just say go from C to D. It's the x values that are complicated here. And so those are the ones that I want to do first, all right? And so what I want then for these here, these are not functions of x, these are functions of y. This is x equals, let's call it g1y, or h1y, even, make it even more of a distinction. And then this, we want to write, if it's not already, as x in terms of a function of y, call it h2y. And so that's what x is going to go between. It's going to go from the lower side is the h1 of y to the upper side, or the right to left to right. Get it right here. Yeah. Okay, and so that's a little bit of a switch, right? Because this is the type 1 region, the y values are functions of x. This is not that. This is what they call a type 2 region. And the distinction is the x values are functions of y. So hopefully you see a little bit of a distinction there, okay? So sometimes it might be advantageous to do it that way instead. All right, and so, if we've got continuity and all that good stuff, here's what that means then. So the way we're going to do this double integral then is do the x's first. So the arrow tells me I'm going to go from this x to this x first. So I'm going to do the h1y, h1 of y to h2 of y. The x's first. Do that first. And then you do the y's, c to d, after that. Okay? So, two ways we could possibly go. All right? So let's do one of those. So let's evaluate the double integral over d, e x over y dA over d equals x comma y. The region is going to be this. So it's 1, it's less than y, it's less than or equal to 2, and then y goes from, x goes between y and y cubed. And it's not, I guess, totally necessary, but let's see if we can draw d out here just to kind of get used to, because sometimes you might have to draw and then get, this is pretty much lined out for us, but it won't always be. So the visual kind of helps here. All right, so in this particular case, we're going from y equals 1 to 2. Now, all right, so the two functions here are x equals y and x equals y cubed. And that one's easy. Y equals x is this. Or x equals y, and then x equals y cubed. It might be more, if we cube root x equals y is more what probably we'd be used to. So it's like this. This. Says you don't necessarily have to draw it, but I think it would cross there. So yeah, this is, so it goes on out there, but this is, so the region I'm talking about is right in here. And yeah, I want to definitely go from this x to this x. Let's write that as x equals 1, so 1 equals that. So I want to go from this x value over to that x value, because then we'll talk about if we didn't do that, what happened on maybe the next example. But anyway, this is what we're doing. It's pretty well, like I said, already spelled out for us here. To do this double integral, yeah, I've got the x's in terms of the y's, so I want to do the x's first. Then the y's, so the interval will be the x's. So go from x equals y lower to y cubed, the upper, and then the y's go from 1 to 2. It's already kind of spelled out on these for us, so you just have to figure out, well, since it's like this, I'd want to do the x's first. All right, so yeah, since we're doing the x's first, let's see what that gets us into here. Yeah, so how am I going to integrate e to the x over y dx? Well, the good news is the y is fixed. It's a constant. So I could think of it, let's think of it this way. Right? I've got e to the 1 over y times x. This is just a number. It's like having a 5x there. And so one way to do this is just with your substitution. You know, it's not just e to the x, because e to the x, the antiderivative is e to the x, but we've got a number times x there, so that's just a simple u substitution. If I let u equal that power there, then that'll make that e to the u, and then e to the u is e to the u. You with me there? All right, so integrate with respect to x, so du then would be, so what would be the derivative of that? Well, I'm doing it with respect to x, so the derivative is just 1 over y, and then dx. So multiply by y du is my dx. What I replace that by, so is that okay? 1 to 2, then I'll do that integral. Now I just got e to the u, and then my dx is y times du. You see that fixed it for me, because now I'm just doing, it's a number times e to the u, so it's just y e to the u, right? Now, let's go back, what was u? U is 1 over y times x, and I'm going to evaluate that from the y to y cubed. Yeah, the big thing here is just keeping straight what, especially when you go to u substitutions, because then you got u's and x's and y's and keep all that straight. But what do I do with these? Where do these go? Those are the x's, yeah. These are the x values. So plug those in. So yeah, they won't always be zeros. One of them will always be zeros. So let's see what we get here. Let's move over here. All right, so we got 1 to 2. So this one goes in for x. So I'll have y e to the 1 over y times x. Well, that x is y cubed. Then I plug the other one in for x. Subtract y 1 over y, y times e 1 over y times y. And I'm going to integrate now to y. After I simplify, of course. So what have I got? 1 to 2, y e to the y squared. That's what I get there. And over here I have minus y e to the, just 1. So you get some, sometimes you get some nice cancellation here. All right, now I need to, so we got to do, the thing about these is you get one integral down, you got to do another one. And that can run into some other things. But good news is on this one, you know, I do want to do these separately, of course. This one is the more complicated one, because this one's just e times y. So that's just going to be a nice little power rule there. What about this one? What are we going to do there? Well, you always run into a lot of those u substitution again, don't you? This one's going to work with u substitution because of the power there being y squared. So yeah, another u substitution, u equals y squared. The du would equal 2y dy, so du over 2y is what dy is. Y e to the u, and du over 2y. Yeah, that's why it works, because then the y's cancel out. So I just have 1/2 e to the u, which is 1/2 e to the u. U is y squared, so 1/2 e to y squared. And then, like I said, that one's a whole lot easier. It's just power rule. It would be e times 1/2 e times 1/2 y squared. 1 to 2. Right, 1 to 2, yeah. So if I plug in those, I've got 1/2 e to the 4th minus 1/2 e times 4. Right, because I plug in the 2 there before. Now plug in the 1, so I have 1/2 e to the 1, and then 1/2 or minus 1/2 e to the 1, or e times 1. Of course, that's just 1/2 e to the 4th. Not much you can do with that. That's 2e there, right? And then look at these. 1/2 e minus 1/2 e. That's the row. So, ta-da. Okay. So it's not, that one's not necessarily hard, it's just a little long. Question or concern? Look okay? Good on that? All right, now, like I said, those, these first couple I've done, they've pretty much had it spelled out. You know, y is going from 1 to 2, x are going from y to y cubed. All right, well, as you probably can already guess, it won't be necessarily always spelled out. Take, for example, double integral over d 4xy minus y cubed dA. And again, dA, we hadn't mentioned that, but dA is just kind of shorthand. You don't know necessarily, they don't spell out whether you do the x's first, but dA is just dx times dy. Just a nice way of writing it in general there. So let's evaluate this double integral over region D, which is the region bounded by y equals square root of x and y equals x cubed. Yeah, okay? So this one, we don't have it all spelled out for us. And that's where, of course, the drawing of D really comes in handy. So that's what I would suggest here, is let's make a little diagram here of D. D is just the region in the XY plane that I'm integrating this over. So it's bounded, all right, so we've got y equals square root of x. It kind of gives a hint maybe of what to do, but actually we could go either way on this one. Y equals square root of x would be, this. And then y equals x cubed. Make it a little larger. This is one there. 0.11 is where they intersect. And so I want to integrate over that region, bounded by both of those. So the region I'm talking about is this little piece right here. Now, like I said, in this case, you could go either way. You could go either way on this one. Probably the way it's spelled out, y equals square root of x, y equals x cubed, that gives me the y values in terms of the x as functions of x, so that's probably how I'd go from this y value up to this y value, but I could do it the other way too, just as easy. I just have to switch those to x equals instead of y equals equation. You see what I'm saying? I could do that, but the way they're specified out here, I would probably say, yeah, let's go from this y value to this y value first. So do the y's first. Then the x's. So it's 4xy minus y cubed. Do the y's first, and then the x's. So if I do the y's first, the y goes from, what's the lower one? X cubed. The lower one's x cubed. And then the upper one is square root of x. Sometimes they say, you might want to write it out like it is over here. In this case, I've got the y's between x cubed, the lower end, and square root of x is the upper end for the y's. And then the x's go from 0 to 1. And so that, whoops. I put a 3 there. I don't know why I put a 3. So anyway, if you write it out like it is in the previous examples, but either way, we're going from x cubed, the lower end of y, to the square root of x is the upper end of y, and then the x is just going from 0 to 1. Okay? Let's see, what do we run into here? We're doing the y's first, so the x's are treated as constants. So that'd just be 4x times 1/2 y squared. And that would be 1/4 y to the 4th. And then that runs from x cubed to square root of x. And again, those go in for the y's. So what have I got? 2x times, all right, so we've got y squared, square root of y, square root of x squared. What is that? It's just x, isn't it? And then put it in there, we'll have minus 1/4, and that's square root of x to the 4th. What happens there? Well, you can think of it as square root of x squared times square root of x squared, and both of those are x. Right? Just x squared. The square root of x to the 4th is x squared. Or however you figure that out. Okay? Good with that? So far so good? Yeah, we plug in for y the x cubed, so we'll have 2x times x cubed squared. That's x to the 6th. You multiply the exponents there. And then minus 1/4 x cubed to the 4th. Well, that's x to the 12th again, because you multiply the exponent. With me there? See where I got all those? Well, notice here I've got 2x squared minus 1/4 x squared. Combine those, that's 8/4 minus 1, that's 7/4 x squared, if you wanted to. I mean, you can do them separately, but I think we should combine them. All right, then we'll have minus, that'll be 2x to the 7th, because you got x to the 1st, x to the 6th. Then you got a minus plus 1/4 x to the 12th. And so now it's yeah, sometimes we run into just basic power rule and antiderivatives, which is this. Okay, so that's 7/4 times 1/3 x cubed minus 2/8 x to the 8th plus 1/4 times 1/13 x to the 13th. And we're going to go that, oh, so we're nice about that, it's just 0 to 1. So plug in the 1, you got 7/12 times 1, that's 1/4 times 1 to the 8th, that's just 1/4, or minus 1/4. And 1/4 times 1/13 is 150, 1 over 52, and 1 to the 13th is 1. And then, yeah, we like it usually when we got zeros because that means all these are zeros. So whatever that is, I get that to be 55 over 156. Okay, so again, that one wasn't hard. It was just, once you get it set up, it's just, you know, that's probably about as short as you could probably hope for, I think, because you're doing two intervals. All right, one more kind of along these same lines. Then we'll talk about one other thing we can do, I need to do. All right, so let's say I'm doing the double integral over region D of 6x squared minus 40y dA. And I want to do that over D where, say it this way, where D is the triangle with vertices 0, 3, 1, 1, and 5, 3. So this one is not at all clear. It doesn't even give me functions. It just gives me, I got a triangle. So that's the fun here we've got. Yeah, again, I would highly recommend here drawing out D in these particular cases. So I've got vertices 0, 3, 1, 1, and 5, 3. So, yeah. Got a nice little triangle, and it's not, we like the ones where they're just cornered right here, but they don't always do that for us. So, yeah, this one's got a little more complicated to it. What do you think? Well, I would probably, because of, these are lines of, have a little slant to them. Probably I'd get a slope intercept form of a line for each one of those. What do you think? Like this one, what would be the y equals mx plus b on it? Let's see. Well, the b is 3. I know that. M, well, I've got it down. Looks like I go down 2 and over 1, -2. So that was pretty nice. Just had to figure out that line. However, in that case, I did it that way. This one is not as nice because I don't have the y-intercept. For one thing, I can get the slope. It looks like what? The run would be 1, 2, 3, 4, and then the rise is 2. So it's a half as the slope. Then I just have to figure out the b, and again, it doesn't turn out to be 0 either, unfortunately. Yeah, just plug in, like we plug in 1, 1 there, get the b. 1 minus a half would be b, which is 1 half. So b is a half too. So however you have to get that secondary line. So this line is that, and then that line is negative 2x plus 3, and this is good because this one's just a horizontal line, y equals 3, but okay. So that's get it started. Yeah, you got this started really yet. All right, so now we've got to figure out how am I going to do this double integral? Do I want to do the y's first, which again, seemingly I've got it y's in terms of x's, so that I may want to do x's first. But maybe not. If I do the x's first, here's the problem. Wouldn't I have to do, so if I go from, do the y's first. If I go from this y up to this y first, I'm going from this line to this line. That's okay. But is that all the way through? Nope. I'd have from this y to this y, so I'd have to break up this region into two. I'd have to do two double integrals. You see what I'm saying? I don't have to, I don't want to, okay? Yeah, I think this one makes much more sense. Again, the picture is worth 1,000 words here, if you can understand what I mean here. It makes more sense because now if I go this way and so this would be this x to this x, I just have to do this x to this x. This line from this to this line, you see? Only one double integral. So that tells me I want to do the x's. The line like this means I go from one x to the other x. I want to do the x's first. Do the x's first. Unfortunately, if I do the x's first, that's not what I've got here for these functions. I've got the y in terms of the x's. I need the x in terms of the y's. It's not that hard to fix, but you see what I'm saying? So I've got to change from y equals mx plus b to x equals whatever. Okay, with me? All right, so what would that be? So I would subtract, subtract 3 and then divide by -2. So I'd probably write that -1/2 y plus 3/2 is what x equals. And then this, let's multiply that by 2. So that'll make that x plus 1. So yeah, it's just 2y. That one works out better. So these are my two x's that go here and here. Now, which one is it? So you go, the lower limit is the one on the left, so it would be the -1/2 y plus 3/2. And then the right one is the upper one, so I think 2y minus 1. And then the good news, the good news is the y's then, we just have to go from the lower y value, which is 1, to the upper y value, which is 3. So those. Is that okay? All right, well, I think this one we get into a little bit of fun. It's not too bad. Okay. All right, so integrate the, so we're doing the x's first. Derivative with respect to, integral with respect to x first. Yeah, so that's x cubed. We got a cubed one. So it'd be 6 divided by 3x cubed. 2x cubed. Now that one doesn't have an x, so it's just minus 40yx. Right? Well, the other bad part about this is now I'm going to plug in these for my x's. But it winds up not being that bad. Do a little u substitution. So that'd be 2 times 2y minus 1 cubed minus 40y times 2y minus 1. And then minus, okay, so here we go. Plug in, and you know, change it to decimal if you want, but you got to plug in those for the x's, so that would be 2x cubed, so that would be 2 times negative 1/2 y plus 3/2 cubed. And then minus 40y times negative 1/2 y plus 3/2. Yeah. All right, so one way to go would be, go ahead and cube that out. Go ahead and cube that out. But another option is, a better option I think, is just do, let's leave this as is and do a u substitution on it. So I'm just going to leave that for now. 2 times 2y minus 1 cubed. And I'm going to do that one, I'm just going to do u substitution. Now here I would go ahead and distribute, that's minus 80y squared plus 40y. Same thing here. I'm just going to leave that as minus 2 times negative 1/2 y. Instead of cubing that out, I can just do a u substitution on that. Now this minus goes with that, so it would be 40y positive times that. So what's that? 40y times that would be negative 20y squared. And again, it's positive 40y times that. Is that 60y? And then, yeah, I've got some like terms here. So like I said, I'm going to leave these two alone and just do those as u substitutions. I've got minus 100y squared. And I've got 100y. Oh, don't forget the negative 2, negative 1/2y plus 3/2 cubed plus 9y. So, yeah, a little bit long, a little bit lengthy, but we're into all sorts of things here. Yeah, let's just do this one with u substitution. U equals 2y. So du would be 2 dy, so all I have to do is divide by 2, which that's going to cancel that 2 out. So I've got 2 times u cubed times du over 2. The 2's canceled. So that's what I'm saying. It's not that bad. It's just 1/4 u to the 4th. Here, and then that's of course 1/4 2y. Oh, 2y minus 1, sorry. To the 4th. All right, then that's just negative 100 thirds y cubed. This again, just another u substitution, negative 1/2 y plus 3/2. So du would be negative 1/2 dy. So negative 2 du is dy. Multiply both sides by negative 2. Anyway, all right, so that gives me the integral would be negative 2 u cubed times negative 2 du. Well, we just got, that's just minus 4 y cubed, or positive 4 actually, isn't it? Minus 2 is positive 4. U to the 3rd, the antiderivative is 1/4, u to the 4th. A line straight here. So that's just going to be u to the 4th, but u is in this case negative 1/2 y plus 3/2 to the 4th. All right, then this one, 100, so it'd be 100 times 1/2 y squared, so it'd be 50 y squared. And do that for 1 to 3. I have a 0 in there. So it'd be 1/4, plug in the 3, you got 5 to the 4th, minus 100 over 3 times 3 cubed is 27. Plug in, so leave that, is that 0? Minus 3/2 plus 3/2, 0. And then 50 times 9. And then plug in the 1s, 2 minus 12 is just 1/4. minus 100 thirds, minus 1/2 plus 3/2, that's 1, which is 1/4. And plus 50. So, yeah, a little messy, but I get that to be negative 935 over 3. Is what I had at one point, some point or another down previously. Is that okay? So again, not hard, just